Okay, so I guess we should get started, right? It is 9:30. Maybe a few more people will join us in time. So let me start by introducing the session just quickly. So welcome everybody to the distributed computing session of ITCS. And I don't want to spoil the talks by telling you what each of the papers is about, but I do want to remark on one thing that I think is really nice about this session. It shows the breadth of the distributed computing field. It shows the various models that we like to study. We have here papers in distributed network algorithms, in massively parallel computing, in shared memory. And we also have some of the really nice connections to various areas in math that we like to make in this field. And there's some very nice representation of that in this session, from graph theory to topology and descriptive combinatorics. And I think that this is one of the things that distinguishes our field, this kind of breadth of areas that we touch upon. So without much ado, let us get started. And Yannic is going to be the first speaker. So I'm going to stop sharing. And Yannic, you can share your screen.
Yes, I will.
Great.
So it works, yes, you can see everything. So let me start, yes. So my name is Yannic Maus, and I will present our paper, Distributed Vertex Cavalry Configuration. So this is joint work with Keren, Censor-Hillel, Shahar, Romem-Peled, and Tigran, Tonoyan. And I won't tell you so much about the distributed and about the model actually, but mostly about the problem that we studied here. So as you can see, we want to go from one vertex cover to another one. But let's start with some motivation. So just assume you have some network and you want to monitor all the links. So maybe you've identified a set of machines which do that for you, but now there's some maintenance needed and you need to change to a different set of machines. So you need to change the monitoring machines. What you want to do here now is while you do the change, you always want to still monitor all links even during the change. So you basically want to have a smooth transition here between the two situations. Each of these situations, monitoring all links, I think that can easily be seen as just the vertex cover. So a subset of the nodes that touches all edges. We'll focus on the transition. And this is a classic problem which has been studied. Normally, this is called sequential, in a sequential setting. The vertex cavalry configuration problem here. You have two vertex covers, so alpha and beta, the blue and the green one. And the goal is to transform one into the other, which means you're supposed to give a reconfiguration schedule that is just a sequence of vertex covers. So each of these CIs here is a vertex cover. This ensures that even in between, you monitor all links. And you're allowed to change one vertex at a time in the classic setting. So you can maybe add the green vertex here, then remove one of the blue ones, then add another one here, remove one, and so on, until you've arrived at your green vertex cover. There are two parameters which are important and tell you about the quality of your schedule. One is the length, but if you restrict yourself to monotone schedules where you can only change each vertex once, and this is what we do in this paper, the length in sequential setting is always the symmetric difference between the two vertex covers. The other parameter is the cost. What's the size of the largest size of one of these intermediate vertex covers? Classic question that has been asked before is, can you even find such a reconfiguration to go from one vertex cover to another one with a certain cost? And this is a difficult problem in general. It's even p-space complete, and even on some restricted graph classes, it remains a hard problem. But there are some exceptions. So in some problems, you can actually reconfigure pretty cheaply in the centralized world. So This is what has been known before and what has been done in the classic setting. But this paper is not about the sequential reconfiguration problem. Instead, what we do is motivated by the distributed setting. So in the distributed setting, you have such a large network, many of these computers, and now you don't want to just change one vertex at a time because there's no global entity controlling this whole network. You don't even know how nodes which are very far away can control their action, decides who adds which vertex first. But instead, you want to change many of the vertices at the same time, maybe add nodes to the vertex cloud which are far apart, remove some. So you want to get some parallelism here. And this is what we call batch reconfiguration. So let's look at the definition. So first, an incomplete definition. So the only change from before is just that we remove the restriction that you can only change one vertex, but we just, you can change many vertices now. But now this causes problems. You could just go from one vertex cover to the other one in just one step, one batch, and you're done. But what does actually happen here? So you put all these vertices, all these changes into one batch. So some of these leave the vertex cover, some other ones appear. So all of them are in one batch. But if you really want to run this on a system, this is not an atomic action to really like do the whole batch, that whole batch as a change. So actually, there is some asynchronous implementation of this. So we as a designer who just put all these vertices into one batch have no control on the order inside a batch. And now what could happen if we just go from one vertex cover to the other one? If you look at an edge here, both of these are in the same batch. Normally we would first add the green one, but now it could happen that first the blue one leaves in this asynchronous implementation, and then one edge is not monitored anymore. We don't want to have that. Another issue that can happen is that the order could be that first all the green ones are added. Then we don't have a problem with monitoring any of the edges. So first all the green ones are added, then the blue ones are removed. But now we, in between, had a very, very large vertex cover. And we also want to avoid that. This is why we ask our batch reconfiguration schedules to be robust. So what we want to do here, we want to have batch reconfiguration schedules so you can reconfigure as many vertices as you want, unbounded number, at the same time. But you need to have the robustness, regardless in which order a batch is executed. You always want to monitor all the links. This is technically you can formulate it as it's written down here, and you also need to pay for the worst case cost if an adversary really implements your batch in a bad order, and this boils down to this condition down here. So this is the problem that we study. And this is actually, so far, like it was motivated by distributed, but it's a problem that is interesting in the centralized world. It's interesting in the distributed world. And you can study it in any setting that you like. And we also do this. And we have quite a large number of results. And I'll just give a very quick overview on some of them because I won't be able to go into depth here. So one is that we can have a generic method to take a sequential schedule and create a batch one, just with a little 1 plus epsilon factor loss in the cost, where epsilon depends on how many batches do you have. And this is also optimal. You cannot improve this. Then we, for certain graph classes, have new sequential schedules and also new batch schedules, and unify some of the proofs for already known sequential schedules. And many of these results come with lower bounds, not all of them. And we, in the sequential world, we have some very short batch schedules where we just use 4 batches for certain graph classes. But then we also have results on the distributed side. That was our initial motivation where we came from. And they're also on certain graph classes. We can compute them very fast, mainly in log star rounds. And we can compute them optimally. The runtime cannot be improved. The approximation factor cannot be improved. Most of these results come with lower bounds. The main tool here for this is what we call a small separator decomposition, which is inspired by network decompositions and padded partitions, but is slightly different and might be of interest for other problems. And what I like about this, I'll talk a bit more about this in the long talk, is that actually using such a decomposition, somehow the goal here is to make different parts of the graph independent. But actually, it turns out for approximation problems, it's not so easy to then just deal with these parts independently. And yeah, I invite you to have a look at the longer talk to see more details on this. So let me not talk about these other results, but just thank you here. And maybe say, just as an open question, all of this here talks about monotone schedules. And I would really like to know what happens in the sequential world, in the centralized world, in the distributed world, what happens if you don't have that? And I don't know. Thank you very much. So happy to take questions.
Yannic. Yeah, we have time for questions.
So Yannic, can I have a question? Do you think you can define the small separator decomposition? Is it easy to do?
Yes, basically, okay, maybe I even have it on the slide somewhere. So maybe then it's easier to follow. Ooh. So basically, you just have these clusters of small diameter, and you have these yellow nodes here, which have in total a large small cardinality. So you have few of these nodes, and for every edge, it should either be inside one of these clusters or have one endpoint here. So you really like the intuition here basically for this vertex cover reconfiguration problem is if you add all the yellow ones to the vertex cover, then all these edges that leave the cluster are covered. So yeah, this is basically
so just a very quick question. So this X, so should I think of it as that it is smaller than like the constant fraction of nodes?
It really depends on the graph class and where we apply it. So it really can be very, very different depending on what you want to have. Yes, it might be a constant fraction of the nodes, but it might be even an absolute small number.
Okay, thanks.
Or like it should relate actually to the it really depends on where you apply it, where you want to apply it. And for this vertex cover reconfiguration problem here, you really want this X to be small in terms of the symmetric difference between your vertex covers, because this basically tells you what opt is. And it should be small in terms of an optimal cost that you need to pay, because you will more or less add all of these yellow vertices here to the vertex cover in between. So it should be small in comparison to your opt. Depending on which problem you study, opt is something different. And this is actually something which we really use that in certain sense. It's not just a constant fraction of the vertices. So depending on which problem you study, you should pick the right X.
Okay, let's move on to the next talk. Thanks a lot, Yannic.
Yes.
So the next talk will be by Quanquan. Can you share your slides and unmute, which I always forget.
Sure, let me share my slides.
Awesome.
Good. Hi everyone. My name is Quanquan, and today I'll be talking about our work on near-optimal distributed implementations of dynamic algorithms for symmetry breaking problems. This is joint work with Shiri, Antaki, and Shay Solomon at Tel Aviv University. And for this short presentation, I'll mainly focus on the motivation, models, and challenges. To give some very broad motivation for our work, real-world networks are often dynamically changing, with new edges being inserted and deleted every second. we show some examples of publicly available datasets, which have millions to even more than 100 billion edges. And private graphs could be even larger, up to trillions of edges. Social networks, in particular, host new connections every second. And on such large graphs with billions of edges, even linear time static algorithms are too expensive to be rerun many times as the graph changes. And this then naturally motivates the study of dynamic graph algorithms, which are traditionally studied in the sequential centralized setting. Unlike static algorithms, dynamic algorithms recompute part of the solution after each update, instead of recomputing the entire solution. And the quality measure we care about for dynamic algorithms is the update time, and the goal is to minimize this update time. One nice aspect of the sequential centralized model, which is the model that traditional dynamic graph algorithms are studied in, is that we can access all of the vertices on one machine. However, on graphs with billions or trillions of edges, the graphs are too large and it takes too much time to compute sequentially on one machine. And so naturally, the focus of the session is, of course, the next step is to split the graph among many different processors or machines, where each node is a processor or a machine, and edges are the communication links between the machines. Nodes can send messages to each other via the edges, and in this paper, we consider the multicast model, where nodes can choose to send the same or different messages to some or all of the nodes. Nodes can also use multiple rounds of communication to send the messages, where in each round they can send messages to the same or different neighbors. The message complexity of a distributed algorithm is the number of messages sent in total over the course of the algorithm. And in this paper, we focus on the congest model, where messages have O of log n size. A problem with sending too many messages is that it can overwhelm the network bandwidth. And I'll talk a bit more about this later on. Another complexity measure we care about, of course, is the round complexity, which is traditionally studied in distributed literature and is defined as the number of rounds the algorithm uses. One problem, again, with having too many rounds is that it takes too long for the algorithm to compute a solution, and it can also result in the algorithm sending too many messages. Distributed networks can also be dynamic, where edges are added and deleted from the network. And such dynamic changes also changes the communication topology of the network. So given these definitions, on these dynamic distributed networks, the grand prize for dynamic distributed algorithms we seek to obtain is to have message complexity that matches the update time of the best known sequential centralized algorithm, while also maintaining O of 1 round complexity. And what's even better is for our algorithms to achieve a robustness against adaptive adversaries. And this is a characteristic we achieve for our algorithms in this paper. So dynamic algorithms are naturally robust against adaptive adversaries, and all of the algorithms presented in our paper are deterministic. A number of previous works have studied dynamic distributed algorithms, but most have focused on minimizing round complexity. And some very recent works have also studied simultaneously handling many concurrent updates. However, the algorithms in these previous works operate by sending messages to all their neighbors via broadcasts. This means that the number of messages required by these algorithms is at least omega of delta, where delta is the maximum degree in the graph. And for sparse graphs, the number of messages sent could be as large as omega of m for sparse graphs, where m is the number of edges in the entire graph. Perhaps surprisingly, very few previous works consider the number of messages sent by the algorithm after dynamic updates as a complexity measure to minimize. There are many practical real-world situations where few messages may be required. Some examples include systems with poor wireless connections, oversaturated networks where many independent agents are on the same network, or a mobile data network in a poorly connected area. Our work focuses on using multicasts for nodes to send messages to a specific subset of neighbors, not all of the neighbors. A few works have studied message complexity, but only for certain problems. Asadi, Onak, Schieber, and Solomon gave an algorithm for MIS. Plague and Solomon study 1 plus epsilon maximum cardinality matching in terms of a graph property called arboricity, denoted by alpha, where alpha could be as large as square root of m in general graphs. And finally, Kaplan and Solomon gave a low out degree orientation algorithm for specifically constant alpha. One natural starting point for developing these dynamic distributed algorithms is to adapt centralized dynamic algorithms to the distributed setting. But there are a number of challenges for adapting these centralized dynamic graph algorithms. First, it is difficult for all nodes to determine the number of edges in the graph if updates on disconnected components of the graph occur. So recall that the edges are also communication links, so there's no way for two disconnected components to talk to each other. And many centralized algorithms use the number of edges in the entire graph as a parameter. Second, many centralized algorithms perform global restarts, where a big portion of the graph recomputes some information. Such a global restart in the distributed setting would mean that information will be propagated throughout much of the network, which could result in both high round and also high message complexity. So while a global restart may not reach every single node in the network, it could still take omega of the diameter number of rounds. And the solution to these challenges is to consider information from the partial local neighborhood, not the entire graph. So using the local neighborhood reduces the round complexity, and using a portion of the local neighborhood or only a partial local neighborhood reduces the message complexity. So using this intuition, we study a number of symmetry breaking graph problems in our paper, including delta plus 1 coloring, maximal matching, 3/2 approximate maximal matching, and maximal independent set. And our algorithms achieve this grand prize up to polylog n factors. So here's a summary of a number of results in our paper for these problems. And our message complexity matches the update time for these problems up to polylog n factors, some of them exactly. And you can refer to our longer talk in our paper for specific details about these algorithms. And I want to spend the last couple of minutes talking more about MIS. As mentioned,
about 1 minute left, just to let you know.
Yeah, thanks. And just to give a quick overview on MIS, as I mentioned previously, Asadi, Onak, Schieber, and Solomon provide a deterministic dynamic distributed MIS algorithm. Their algorithm uses m to the 3/4 amortized vestiges and O of 1 amortized rounds. But their algorithm uses one crucial characteristic of the graph, which is that the graph remains connected throughout all the updates. So compared to our result, we improve the message complexity polynomially while only paying a polylog n factor in the number of rounds. And most importantly, we obtain our result without using any connectivity assumptions. And the starting point of this result builds upon the sequential centralized dynamic MIS algorithm of Gupta and Khan. And just very quickly, the Gupta and Khan algorithm prioritizes membership in the MIS to low degree nodes, which means that low degree nodes are added to the MIS first before adding high degree nodes. High degree nodes are only added to MIS after processing the low degree nodes. And the main part of the Gupta and Khan algorithm is that they do a global restart on all the high degree nodes after each update step to determine which high degree nodes to add to the graph. So there's naturally a couple of challenges for distributing this algorithm. The first challenge is, how do you determine the high degree and low degree nodes if the number of edges in the graph is unknown? The second challenge is, how do we perform a global restart efficiently. And the solution to the second challenge is that instead of a global restart, we instead do a local restart. And I encourage you to watch our longer talk for how specifically we solve these challenges. And I just want to conclude with, we initialize a formal study of message-efficient dynamic algorithms in distributed network, and we achieved this grand prize for several fundamental graph problems up to polylog n factors. There are a number of interesting questions that is a result of our study, and we think these questions will be interesting to explore in future work. So this concludes the presentation. I'm happy to take any questions if there's still time left.
Thanks a lot. I think while the next speaker sets up, Hugo, we can take a quick question if anyone has one. Hugo, do you want to share your slides?
Yes.
Cool. Okay. All right, thanks a lot.
Thank you.
Can you hear me?
Yeah, definitely.
Okay. So hello, everyone, and thank you for attending. So first of all, I will talk about the distributed systems model that we are considering. We are considering a finite set of processes with a communication model of shared memory. This means that each process has its own memory slot to which it can write, but they can read the whole shared memory. And we are allowing processes to crash. This means that processes can stop their execution at any time and they will never recover from this crash. And we are considering asynchronous wait-free distributed models, which means that each process runs at its own time and it does not need the other processes to progress in order to do work. In particular, we are interested in task solvability. So for example, consensus, approximate agreement, among other tasks. I will talk a bit about combinatorial topology. So I will start with simplices. So simplices are simply multi-dimensional triangles that are defined by a finite set of vertices. And we can glue together these simplices to form more elaborate structures called simplicial complexes. An interesting thing is that if we interpret simplices as a finely generated spaces, then we have a geometric interpretation for the whole simplicial complex. And now I will go into the topological modeling of distributed systems. So the idea is that we want to construct a simplicial complex from the distributed system model in order to be able to express non-trivial features as topological properties. And the way that we do it is that we use local states to define vertices, we use global states to define faces, and we use the indistinguishability relation between these global states to decide how the faces intersect. So to show an example, here is a two-process wait-free shared memory model. So there are basically three different possibilities. Either the green process is faster, which is this one that I'm highlighting, or the red process is faster, which is highlighted here, or both are more or less execute at the same time, which is this execution. As you can notice, the execution where the green process is faster is indistinguishable for the execution where both execute at more or less the same time for the red process, because the red process cannot tell or not whether the green process has received its input value. And therefore they are connected by this red vertex. So in order to capture how the communication transforms a distributed system, we use a sequence of simplicial complexes, which we call the protocol complex, P0, P1 up to Pk, one per round. And the idea is that communication transforms the K round protocol complex into the K+1 protocol complex. And an interesting property is that in the wait-free shared memory model, in particular in the iterated immediate snapshot model, which we are using, each communication round basically subdivides the input complex. So to take a look to what that means, so here is an example of a three-process wait-free shared memory protocol complex. This is the protocol complex at round 0. So at round 0, no process has communicated, and they are only aware of their own input values, which is represented by this simplex. However, after one round of communication, there are many more different possibilities. You can see that the vertices in the corners correspond to processes that were very fast, and therefore they were not able to learn any input from any other processes. Meanwhile, the processes that are in the middle are processes that were able to learn all of the input values from all of the other processes, and the rest, like these two, correspond to processes in executions that were able to learn only one of the input values. So this is captured more precisely by the asynchronous computability theorem, that is due to Herlihy and Shabi, which is a characterization of asynchronous shared memory computability in terms of chromatic subdivision and the existence of simplicial maps that preserve the validity conditions established by delta. So I'm ready now to talk about our contributions in our paper. So we define continuous tasks and chromatic functions. Then we show that chromatic functions have a chromatic version of the simplicial approximation theorem, which then allows us to give a complete characterization of the weight-free task solvability in terms of continuity and color preservation properties. And as an extra, we have that we can use continuous tasks to specify density requirements. So the asynchronous computability theorem matches task solvability to simplicial maps and subdivisions. And at the same time, the simplicial approximation theorem matches continuous function to subdivision and simplicial maps. So a natural question that one can ask is whether or not we can tie these two together and match task solvability to continuous functions. And the answer is yes, but the continuity condition is not enough. And why? Well, take a look at the hourglass task shown here. The hourglass task is not solvable in weight-free shared memory. However, there is a continuous function that matches the validity condition delta. So what is happening here? Well, we should notice that any continuous function that matches the validity condition delta doesn't preserve the color structure. And also, any simplicial map that preserves the validity condition delta also must collapse part of the simplicial complex. Like it is shown in this picture, these vertices will be collapsed into this single vertex. So in order to overcome these obstacles, we give a definition that restricts the behavior of continuous function, which is, and this is the formal definition, but basically this ensures that a function does not collapse and it forces it to respect the color structure. And the nice thing about this condition is that any function that satisfies this condition has a chromatic approximation. And then later we show that these functions that have a chromatic approximation match exactly tasks that are solvable in the asynchronous weight-free shared memory model. So I will give a brief visual sketch of the proof of the chromatic approximation. So the idea is to subdivide the input complex until simplices are very small, and we can guarantee that they fall inside of a star at the image. We can do this via the Lebesgue number theorem. And then once we guarantee that, then we look at the center of the star and we match the vertex of the corresponding color, which in this case is the yellow vertex, and we map it to the center of the star. We do this because then this allows us to project and get rid of one color, like here in this picture. And because we can get rid of one color, then we can project, and this reduces the dimension of both the input complex and the output complex, and this enables us to apply induction and repeat the same operation over and over again until we have a very simple problem to solve. And then we can use the lower dimensional solutions to have higher dimensional solutions just by keeping track of which were the vertices that were mapped to the centers of the stars. And at the end, we join all of these partial solutions to build a global approximation. So in conclusion, in the paper, we show that task solvability in the weight-free shared memory model is essentially a topological and a color-preserving property. And we can use these chromatic functions to define continuous tasks, because continuous tasks are now one-to-one matched to the tasks that are solvable in weight-free shared memory. And also, chromatic functions are exactly the functions that allow a chromatic simplicial approximation. And we also explain this correspondence. And one extra thing that we can find in the paper is an interesting application, which is that we can use continuous tasks to specify further requirements. So for example, the thing that I was mentioning before about density is that, for example, approximate agreement, we can specify an approximate agreement which results in at least 99% or any percentage that we want that will result in exact agreement. So that is all, and thank you very much. Do you have any questions?
Yeah, we do have time for some questions.
Yes.
So what do you think that your work leaves open in this arena? If anything?
So I think that what is open what is left open is whether or not we can also use these continuous functions to other distributed system models. Mm-hmm. So, for example, in the one strong assumption in the weight-free shared memory model is the assumption that the systems have that they have compact communication models. So this means that there is a fixed round by which all processes must decide. This is because of the weight freedom. However, there are many models that do not have this compact property, this compactness property. And here it's we are in a way thinking that there will always be a fixed round, and we want to extend this to in that direction. And also we want to think about streaming protocols, so or stabilization protocols. So maybe we want to think about not only having an input and having an output, but having also some eventuality condition and other properties.
Very interesting. All right, let's move on. Let's thank Hugo for the talk and move on to the next talk, which will be by Vacek. So Hugo, if you could, oh, great.
Hello, everybody, can you hear me?
We can hear you, but it was better before when we were talking before the session. I don't know what you changed.
Is it now better?
Yeah, it became better again.
Okay, yeah, sorry. Yeah, so if it becomes worse again, then please tell me. Yeah, so hello, everybody. So I will try to keep my talk short. So let me jump to the summary. Okay, so, you know, in computer science and distributed algorithms, we have all of those models that we study, right? And one of those simple models is the so-called Rotem model of distributed computing. And then there is this field in infinite mathematics called descriptive combinatorics, where mathematicians study certain local constructions, so to say. So kind of both of these fields study local constructions, so there could maybe be some kind of connection between them. And it turns out that indeed there is a connection. There are some, I would say, pretty interesting connections between these two fields. And we are not the first ones to basically come up with this idea. So Anton Bernstein came up with this idea, and in this paper we basically try to push these ideas further. So I need to quickly start by defining this local model of computing, right? So this is a very old distributed model, very simple. So we just have this huge undirected graph on n nodes. We think of each node as being a computer. And now to make things super simple, we just assume that the computers are communicating in synchronous message passing rounds. The messages can be unbounded. Also, the computation that happens inside the computers is unbounded. So everything is very simple. At the beginning of the algorithm, the computers know only some basic information, like how many nodes there are. And in the end, everybody should know it's part of the output. For example, if you want to color the network, everybody should know its color. And the time complexity, again, very simple. It's just the number of rounds. So in this talk, we will actually make things even much more simple. We will just talk about graphs that have constant degree, and they are actually just regular trees. Okay, so everything's super simple. It actually makes sense to consider this class of regular trees because this class is already captures a lot of the difficulties in this local model. So the cool stuff about the local model is that we actually know a lot. Okay, so there was like really a lot of progress in the past 10 years. And for example, here is one thing that we understand. So if you really restrict yourself to these delta regular trees, and if you also restrict yourself to a large class of problems that we call local problems, like these examples, then we actually understand that all of those problems are in one of the 5 buckets. Each problem is one of the 5 types, which I think is really amazing. So for example, we know that like one bucket are problems that you can solve in log and rounds, either deterministic or randomized. Another bucket, log and randomized rounds, but log and deterministic, and so on. So I think this is really amazing because, for example, if you tell me that you have an algorithm for your favorite local problem that runs in log square rounds, then I can automatically tell you, okay, but I have faster algorithm that needs only log and rounds. Okay, so we really understand a lot. Okay, so okay, now for something completely different. So what is this descriptive combinatorics? I just want to give you an example. So here is a riddle. I give you a square sheet of paper and scissors, and I ask you to cut this square into some pieces, and then just rearrange these pieces, just basically shift them so that they form a circle of the same area. I mean, this is clearly impossible, right? If these pieces are somehow like well enough behaved, then I mean, this just has to be impossible, right? But what if the pieces are measurable? So measurable is somehow like one of the basic conditions, one of the basic notions that people in math study, right? So actually, it turns out, quite surprisingly, that then the answer is yes. That you can really kind of cut the square into something like 10 to the, I don't know, 300 or something pieces. And each of these pieces will be really something super complicated, right? And then you just shift these pieces and you get a circle. And somehow the way how mathematicians constructed this thing is actually using some kind of local constructions inside. They are actually kind of reducing it to some kind of matching or flow problem. And it turns out that somehow these type of constructions are actually pretty similar to this distributed local model that we are studying. And this is exactly what this descriptive combinatorics is about. So now I will kind of jump to kind of the main point of the paper, or kind of what is our contribution. So we basically try to study these things like, complexity theory. But, in the local model, I already told you that we now understand that we have these 5 complexity classes. And we understand that every problem is in one of these 5 buckets, right? But also in this descriptive combinatorics, you can have some like pretty natural definitions. You can want to construct so-called Borel solutions or measurable solutions. I mean, it's defined totally differently than in distributed computing. These are like some very abstract definitions, but these are, really some well-studied, well-defined complexity classes. But by the way, there is also this field of factors of IIDs. I don't want to talk about it now to keep things kind of simple. So basically what we try to do is we try to do what people in complexity theory are doing, right? We just try to define as many classes as we can, and then to prove as many inclusions as we can, right? So this is somehow like the picture of what we are trying to do. So also in the paper, we introduced some new tricks that were already again used in some subsequent works to get some new results, both in the field of distributed algorithms and descriptive combinatorics, but there is no time to go over this thing. So let me just try to conclude. So it feels that this is really an exciting area. and there is a lot of things waiting to be discovered. And I hope that I kind of conveyed at least part of my excitement about this whole thing. And also big thanks to Rotem for chairing the session, and Mark for organizing, and all of the other organizers. Okay, thank you.
Thanks a lot. We have a few more minutes, and I wonder if you, if it's possible. I know it's a very deep paper, but I wonder if it's possible to say something a bit more concrete about the kind of results that you get.
Mm-hmm. Okay, yeah. So thank you. So I can, for example, go to this picture, right? So I can just give you an example of an arrow from the paper, right? So for example, here is an arrow that has actually two connections. So it is actually proving that this class of local O of log n, these are all the problems that you can solve with a local algorithm with log n rounds, either distributed or randomized. So sorry, either deterministic or randomized. So this class is actually exactly the same as this class of so-called bare measurable solutions. So this is kind of a very abstract class. I'm sorry that there is no way I can kind of define these things. One of the reasons is that I actually frankly don't understand like that much these formal definitions. Somehow when we work with it, we usually have some kind of, so for example, when we work with this class, we actually have some kind of combinatorial understanding of what are kind of the constructions that you can do in these classes. Okay, so somehow, these things, they are defined very abstractly, but when you work with them, then oftentimes you have some kind of combinatorial ways of understanding them. So I think, for example, this is something that I find very surprising for several reasons. One of the reasons is that really you kind of get the equality of classes, right? You have this concept that you can define in distributed algorithms. This O of log n, it feels kind of arbitrary, right? I mean, why log n? Why not something different? And this thing, it actually, this is something that talks about infinite graphs. So I didn't want to go into details, but all of these things, they talk about infinite graphs. It talks about infinite trees. And there is no way of measuring something as a function of n because there is no n, everything's infinite. So I kind of feel like that it's really interesting that it kind of matches, right? So I try to talk a bit more exactly about this thing in the longer version of the video. So maybe the best I can say is, yeah, maybe try to look there.
Yeah, thanks a lot. I appreciate that doing this in 10 minutes is a mission impossible. Does anybody have another question maybe in the 1 minute that we have left for the talk?
Well, yeah. I wonder if you could say something about what would require to go beyond trees. Yeah.
Mm-hmm. Yeah, so for example, we have also, for example, another paper that tries to study, again, grids, like very, very simple graph, right? Like, think of like 2D grids or something like that. So this is, again, very simple graph, but actually things are behaving quite differently. We again, kind of draw a picture where we have all of these classes, but now the arrows are actually a bit different. So that there are still some interesting things you can prove, but some of them are actually a bit different. So yeah, so basically currently we understand, I would say quite well, these like very concrete things like trees or grids. And we have some general understanding of general graphs. I mean, when we talk about graphs, we always mean constant degree graphs, which is already kind of a big restriction, I guess, if you, for example, care about distributed algorithms. But there is something for constant degree for all constant degree graphs. For example, we understand that this is just an example that this class here is always subset of that class here. Actually, this equality of local log star and equal continuous, this holds very generally. This is like a very general phenomenon. So we understand that some things are like very general phenomena, but currently I feel like it kind of makes sense to really look at these like very simple examples, like trees, they are the expanding graphs, grids, these are the graphs of small growth. And even there, it feels like that there is lots that we don't understand. Yeah, so thank you for the question, that's very good.
Okay, thanks a lot. So let's go to the last talk of the session, which will be by Marina, and this is going to be again something completely different from the most abstract paper in the session to one of the most practical contributions that we have today.
Hey, can everyone see my screen? Okay, so yeah, my name is Marina, and I'll be talking about adaptive massively parallel constant round tree contraction. So tree contractions are very general tools for solving a wide range of problems on trees. The idea is basically you take components of your tree and contract them into vertices, and you do this iteratively until T itself is a single vertex. Now, this process must exhibit some properties. First of all, the contraction must be efficient and reversible. And in addition, when we contract components, we're going to be tagging the vertices with some sort of data that represents the previous component, such that we don't lose too much information. We still want to be able to solve the initial problem on the initial tree. And the condition here is that that data that we require must be space efficient. And that's what space efficient means kind of depends on your model of computation. Okay, so tree contractions have been applied to a number of applications, including circuit evaluation, finding planar graph separators, approximating tree width, and many more. There's a lot of literature on this. It's a very widely usable tool. So tree contractions were first introduced in 1985 by Miller and Rafe. They used the PRAM model of computation, which is parallel random access memory. The gist of that, for those of you who don't know, is basically you have a bunch of little processors doing independent operations, and you're interested in how long the process takes, and they're allowed to communicate all the time, basically. So they showed that their algorithm requires O of log n PRAM time, and this has been improved over the years, but we still have the O of log n time requirement on those algorithms. So let's just talk briefly about how tree contractions work. They go over a number of phases, and in each phase, they have two stages. So the first stage is going to be compress. In compress, you're going to contract some number of internal connected components that you identify. So for instance, in Miller and Rafe's algorithm, they would look at long chains of vertices with only one child and contract every other vertex into its parent. So on the tree example I have here, that would look something like this. The next stage is going to be rake, where we just contract all leaves into their parents. And that's going to look something like this. So again, O of log n time hasn't been broken since 1985. We're going to be looking at a different model computation where we can break this complexity barrier, in fact, by a very significant margin. However, I will note that we're looking at round complexity in a distributed model of computation, which is not 100% analogous to time complexity, but they are very similar and they kind of translate between models in interesting ways. So let's take a look at the model of computation. We'll be using adaptive massively parallel computation, or AMPC. For those of you who don't know, AMPC is the successor to MPC, which is a popular model of computation that's been used over the past decade. AMPC was introduced a few years ago, so it's a very new area. It's been shown to be able to solve some things we don't think that MPC can do. It's strictly stronger than MPC, and it also is still highly practical. It can be implemented on existing systems. So in AMPC, we have this notion of a distributed hash table, which is just a large data structure that you have simultaneous, parallel read and write access to. But it's restricted in specific ways, you'll see in a second. AMPC computation proceeds in rounds. In each round, you have a number of processors executing local computations. They are allowed to read from the previous distributed hash table and write to the next one. So obviously, in a round, no messages can be passed between machines. This proceeds over some number of rounds. The input to the problem is stored on the first distributed hash table, and the output must be found on the final one. So this is how it works. Machines aren't associated with vertices or anything, but oftentimes you will associate them with vertices. So the complexity of interest here is the round complexity, which can be thought of as a measurement of the number of times that machines can communicate, i.e. a machine can only send a message from it to another machine in between rounds. We're also interested in some space complexities. We specifically use the low memory model of computation, where we only have O of n to the epsilon space per machine for epsilon between 0 and 1. That's a highly restrictive regime because you can't even store the neighborhood of a vertex for some vertices. And the total memory must just not blow up. So it must be linear in the problem size at any given time. Okay, so that's a high level of AMPC. Let's talk about some existing AMPC algorithms, some of which we'll use and some of it we'll compare our results to. So we're going to use a number of existing algorithms executing processes on forests. These all have been shown to require only O of 1 over epsilon AMPC rounds. This is highly efficient because we generally assume epsilon is a constant, at least with respect to n. We still want to optimize in terms of epsilon, but it's much smaller than any dependency on n. It is conjectured that these require omega of log n MPC rounds, and that's why we use AMPC. Our results are the following two algorithms, which are both execute tree contractions. The first is on trees of bounded degree, that is max degree n to the epsilon. And it only requires O of 1 over epsilon squared rounds. And this can be used as a subroutine for our general algorithm, which requires O of 1 over epsilon cubed rounds. Okay, so those are two like main general results, but we also show a number of applications. And let's compare them to some existing AMPC algorithms. So first, we show that our first algorithm on bounded degree trees can actually be used to solve some general problems. So maximal matching and maximal independent set on general trees can be transformed into problems on bounded degree trees, so we can apply our more efficient algorithm to them and get constant round algorithms. However, there do exist algorithms already that solve maximal matching and independent set in O of 1 rounds in AMPC, so we don't beat this. However, we think this is an interesting tool moving forward. In addition, we look at maximum weighted and cardinality matching, which both of them we can solve in O of 1 over epsilon cubed rounds on trees. This beats O of log n rounds from previous algorithms. Also note that we get a much better approximation for maximum weight matching. Again, the caveat here is that these are only on trees. And then some previously unexplored problems, maximum weighted independent set and tree isomorphism can also be solved in O of 1 over epsilon cubed rounds on trees. Okay, so I'm going to quickly go over some of our algorithms. So let's start with our algorithm on bounded degree trees. Recall that tree contractions requires two stages, compress and rake. And let's talk about compress first. We're going to compress according to what we call the preorder decomposition, which is a partition of vertices such that each group in the partition, the order of the groups in the partition agrees with the preorder traversal of the vertices. Additionally, we have a bound on the sum of the degrees of the vertices in each group, which just will help us with our space constraints. To compress, we contract connected components induced by each group. So we can see an example of this process here where vertices are labeled with their groups. Note that this may seem difficult to deal with because, for instance, group 2 in this case is not reduced at all. We have 3 isolated vertices to start and 3 isolated vertices to end. However, we can show some nice properties of this process. First, as long as the max degree of the tree is bounded, as we've talked about, we can find a preorder decomposition with only O of n to the 1 minus epsilon groups. Additionally, because of the properties of the preorder traversal, we can argue that there's at most one internal node per group. And you can see that at least in this example. So given these two properties, we can show that there are at most k internal nodes and k is at most O of n to the 1 minus epsilon. So when we rake, we end up with a tree that is just the vertices in the tree are just the internal nodes that occurred after we compressed. Therefore, the resulting tree has only size O of n to the 1 minus epsilon. Thus, we can complete this in O of 1 over epsilon phases. Each phase, we have to do a preorder traversal, which is O of 1 over epsilon rounds, so we get a O of 1 over epsilon squared algorithm. So that's our first result. The second result, it actually kind of follows a similar model. So to compress, we start by getting rid of high degree vertices, because those are annoying. Second, we're going to take all of the remaining trees in this forest we created, which are all low degree, and apply our previous algorithm. Therefore, each tree in the forest is contracted into a single vertex. Then we simply add the high degree vertices back in. And that's going to look something like this. We get some nice properties. For instance, no small component is going to be the parent of another small component, and that's just by maximality of the connected components. And this is a key feature that allows us to argue that after compression, at most, an O of n to the 1 minus epsilon fraction of vertices are internal nodes. So this actually leads to the exact same argument we had before. O of n to the 1 minus epsilon internal nodes. We rake all the leaves away, so we get an O of n to the 1 minus epsilon vertex tree. So we take only 1 over epsilon phases. Since we apply our previous algorithm each time we compress, we end up with an O of 1 over epsilon cubed algorithm. So it's just like a nice process that like worked out quite like interestingly. There's obviously a lot of complexity that gets added when you also go to apply this to real applications. There's still a lot to show for the specific applications, but I'll have to defer that to the paper. So I'd like to thank my co-authors and as well as the people organizing ITCS. Thank you.
Wonderful, thanks a lot. Anybody have a quick question?
I have two quick questions. One is, can you give a pointer to the conjecture of log n in the standard MPC model, or maybe write it in the chat?
It's called
somehow,
the 1 versus 2 cycle conjecture.
Yes, okay. So this is the same. Okay. Then
yep, you got that? Okay, cool.
Okay. Okay, the other one, does this model make sense in a deterministic way?
Does this model make sense in a deterministic way? As in, can
I
you
guess
develop
yes.
as in, can you develop deterministic algorithms for AMPC? Okay, so I think much of the existing algorithms use random procedures. So there's a lot of like little things you have to do in MPC and AMPC that you kind of like gloss over when you talk about higher level algorithms, like methods to like ensure the right input gets to the right machine. I kind of forget if those require random processes. If they do require random processes, then a lot of basic operations that you want to do, you can't do. Otherwise,
I think these work. Like, I just wonder about the hash tables and
the distributed hash tables. I am not familiar with the implementation of distributed hash tables, so I do not know. I would expect they require some sort of randomness to work properly.
Okay, so I do see one question in the chat by Nicole. I know we're over time for the session, but I think whoever wants to stay can stay for this question. Nicole, do you want to ask your question?
I can also read it here.
Yeah.
So the question is, have trees contractions found uses for classes of graphs more general than trees, e.g. graphs of bounded arboricity? So the answer would be yes on graphs of bounded tree width. So you can actually use the original tree contraction algorithm in Pram to find actually a tree decomposition for graphs of bounded tree width, and then you can just apply the algorithm on top of that. It's still like something that you need to like. There's other things that are involved in that algorithm, so I can't just say that we can use these algorithms that way. Bounded arboricity, maybe there's some nice decomposition you get with bounded arboricity graphs, but I don't know. I don't think I haven't witnessed like the original algorithms being used for bounded arboricity graphs, but there might be some literature out there.
Very nice. All right. Thanks to all the speakers in the session, and see you in the remaining sessions of ITCS.